Alright, hi everybody. This is a video discussing friction and Newton's laws. This is meant to be sort of an introduction to the topic. I'm going to do a later one that's going to do some sample problems that you can mess around with. But as we talked about in class, when you're talking about friction, there's really two different flavors of friction, and we can kind of envision this. If you imagine that, let's say, you're helping some friend of yours push a, let's make it a refrigerator, not a little refrigerator, a big refrigerator. You are here helping this poor dude. What do legs look like? Something, I don't know. Okay, so here you are. You're pushing on this refrigerator, and what you'll notice is that as you push on this thing, you're going to apply some sort of force. And if it's not moving, that must mean there is a force being applied back in the opposite direction, and that force would be friction. And you would keep pushing and keep pushing, and then suddenly you'd find that this refrigerator would pop free, and then it would start moving, and everything would move in that direction, and it would feel actually easier once things got moving, that easier to move this thing. So that's actually kind of implies you can do the same trick with your hand on the surface of the desk. If you push your hand on the surface of the desk, you'll find that it sort of sticks and then kind of pops free as it slides across the table. And that's because there are two different flavors to friction, and the first one, where this refrigerator's not moving, we call that static friction. Static friction deals with anything that's not, where the two surfaces are not moving with respect to each other. Some examples of that would be really normal tire operation, and by that I mean when your tires are not skidding, when they're doing what they're supposed to do. And engineers are very precise about using, making sure that your tires are not skidding. That's the whole point of anti-lock brakes. So when the car moves and it's the interface between the tire and the road does not. So that's an example of static friction. And of course, this example we have right here, pushing on something heavy that just won't budge. The thing that's fighting you is static friction. But once it does get moving, we're dealing with kinetic friction. And kinetic friction, you can experience that. Just rub your hands together. That's kinetic friction. Slide your hands across the floor. Also, when your tires are skidding, so skidding tires is an example of where the two surfaces in contact are sliding across each other. And we're going to find out that with the exception of very exotic materials, kinetic friction will always be less than static friction. So once two things are moving with respect to each other, you have less friction. That is why skidding tires is bad. That's why you have what's called anti-lock brakes, because you want to have your tires in static contact with the road. And okay, so that kind of sets the stage a little bit. What about thinking about this friction force? Is there some formula that we can come up for this so that we can unpack this a little bit and think about what's going on? Well, there is, of course. You've seen it in class. And the way we do this is we talk about the friction force. We'd have to have a separate, let me get all fancy here. I'm going to use colors. So let's say let's do kinetic first. I'm going to do kinetic friction. The force of friction, kinetic, that's what that subscript is going to be a constant value. And once the thing gets moving, it's going to be a constant value, and it's some number here times the normal force of the object. Okay, so you can think of this number. If this number was 0.3, it would be 30% of the normal force. Or if it was 0.7, it'd be 70% of the normal force. So the number is just a special number to tell you how much of the normal force the kinetic friction force is, and we use a special symbol for this. It's mu. That is actually a Greek letter. It's this funny looking U. And when we're talking about kinetic friction, we'll usually put a little prefix there, or subscript, I mean, for this. So if you ever want to find this friction force, you'd need to know this coefficient of kinetic friction. That's what we call that guy. Coefficient of kinetic friction. You would need to know that, and the normal force of the object. Okay, well that's one thing. Well, what about static friction? Well, static friction is kind of an interesting scenario because, if I'm not pushing on this refrigerator, the static friction is nothing. it's not going to push back unless I'm pushing on it. But if I give it a little nudge to the right, static friction will give it a little nudge to fight my nudge. And if I keep pushing it harder and harder, static friction is going to grow. So I can't really say that my static friction is an equality. You know, I can't say that F of static friction is going to be equal to something, but I could say that it is less than or equal to something. I could use an inequality here, and for that it's going to look a lot like this. It is some percentage of the normal force, and in fact we use a mu sub s to represent that. So this guy is the coefficient, if I can spell, of static friction, and that is the formula we want to use for that. So these two coefficients are pretty important, and in fact it turns out that these coefficients, these numbers, what they depend upon are the two materials in contact. So they depend on the materials in contact. So what you would need to do typically is look this up. Look up in a chart like the one I've got right here, the one we saw in class, and you would look at the two materials in contact and see what the static friction is and what the kinetic friction is. And what you'll notice here is that for, I think, everything, the kinetic friction coefficient is less than the static friction coefficient. That is to say, it's harder to get something moving than it is to keep it moving, right? And you see some very interesting things here. First of all, things like metal on metal, like steel on steel, has a pretty high static coefficient of friction. But if I put a single little drop of oil, like I have down here, metal on metal lubricated, it drops way, 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 way down, which is the reason you have oil in your car. You don't want these pieces of metal rubbing against each other. You might also see things like rubber on concrete, which has a very good, very high static coefficient of friction, but on wet concrete, not so great. This is important if you are a tire manufacturer and you're making tires that are running on dry concrete or wet. You want to make sure that you're well aware of the frictional force you're getting, and that's why you slip. You tend to slip when it rains because your friction is much, much less. We see it right there. Okay, now the other little piece here, of course, is the normal force. We'll see some of that in example problems. A lot of times, for the problems we're dealing with in this class, the normal force will be equal to mg, but not always, so just be aware of that. Another way to think about these equations is to think about it in terms of a graph. If I am plotting friction force versus, so in newtons, versus whatever, I can just call it time for the sake of this. What I'll find is that if I'm pushing on an object, it is going to fight it and fight it and fight it and fight it, and then all of a sudden, boom, it's going to kind of fall off the edge of a cliff here. And what I'm referring to here is this transition point, this breakaway point. Basically, during this portion of the motion, the object was not moving. But once we got over here, sort of after this breakaway point, we're dealing with an object that is moving. We're dealing with kinetic friction. So what I would call this right here is this magical little point right here is the breakaway point. And this value that corresponds to is my maximum static friction force. Right, so that is the equal to part of this greater than or less than or equal to. Now this part, what is this? Well, this is just my kinetic friction. So this is the value mu sub k times the normal force. That's what this is. That's what that value is. So whatever that reads over here on the axis. And you can see, so here we see definitely static friction is greater than kinetic friction. And again, it's a little tricky sometimes to be thinking about this, and what I would encourage you to do is just kind of draw out for yourself. Just think, okay, let's say I have a box and I'm applying a certain force here. Let's see what happens to this box. Well, if I apply a little force, ooh, what happened to you? You just disappeared. If I apply a little force there, well then friction's going to fight me, right? If I apply a little bit more force, friction's going to grow. So friction's never going to be more than my applied force. If it were, this box would crawl around to the left, which would be weird, and it doesn't do that. If I apply, you know, a little bit more force, at some point I'm going to reach a point where this frictional force can't be anymore. It wants to cancel out my applied force, but there is a friction static maximum that it cannot exceed. And for this point, for this one right here, I might be switching colors in weird ways, but this is not moving. And then at some magical point, this box is going to start moving this way with an acceleration. And what that means is that, okay, what I've done, if I reach this point, if I give it just a tiny bit nudge more, this applied force is now caused this to break free, and I'm not dealing with static friction anymore. I'm dealing with kinetic friction, which, if you notice, I drew a smaller arrow. That means that this is smaller force than this, so I am going to have a net force to the right. So for this particular example, I am moving and accelerating, right? Because I have a net force. And that's what's happening. So you'll notice this when you play with this in the lab, that you're going to start moving and accelerating. If I want this thing not to accelerate, I got to keep it moving but reduce my applied force so that it just equals this static friction, or sorry, kinetic friction force. So I actually have to reduce this applied force to make it not accelerate. If I maintain the force that broke it free, I'll keep accelerating, and that's why things kind of feel like they jump when they break free of friction, because all of a sudden you've exceeded the force and you're accelerating, so you tend to sort of, whoa, you know, it kind of jumps out in front of you. So anyway, just covering some big ideas there. I think that some of the key ideas that we talk about when we talk about friction, it's been that force that has been plaguing us for a very long time and messing up the works, so it's important to have a good feel for it, and I hope this helps.